Okay. Well, first of all, thank you for this opportunity. It's my honor to share my research with you. As Sharon mentioned, my name is Sean Bell. I go by XB Hu. I'm assistant professor at Missouri University of Science and Technology. And the topic I'm going to present today is the development and the testing of autonomous maintenance technology for transportation infrastructure maintenance. Or if you want to memorize this in short, it is CAV for work zone maintenance. So before my presentation today, I want to acknowledge the following organization and people that support my research. From Missouri DOT, Chris Redline, Jimmy Shannon, and Jim Harper. And from Colorado DOT, Tyler Wyden, Ashley Nyland, and David Reeves. And also, Sedalia is leading an ANT pool fund with 12 state DOT members. From Kratos Manufacturer and US DOT Mid-America Transportation Center, as well as this national UTC, National Center for Transportation Infrastructure Durability and Life Extension. And also, I have a few students at the Missouri SNT that are supporting me. They are Qing Tang and Yinchu Chen. So with that, I'm going to start my presentation today. Today, I hope to touch base on 4 aspects with you. In the first section, I hope to present the technology that we are doing research on at the work zone locations. And next, I will talk about the system testing and evaluation. How can we claim that the technology works well, and what is the industry standard? And thirdly is a system operational design domain, or in short, ODD, according to US DOT. And lastly, I will talk about the driver operation guideline. Basically, how can the driver operate this new animal, this new technology? So with that, I'm gonna start my presentation today, and I want to start actually with a story. And this is a real story. It is about an engineer called Michael Suber. And Michael is it's a husband and it's a father, and he's also a Missouri DOT maintenance worker. There was an interview. An interview was performed in January 2017, and Michael said that he was patching potholes on the US 50. That's his day job, right? That's his maintenance worker. That's his head. And he said, I was following the pothole patcher, and I noticed a truck coming really close to me. So I hit my panic light on and to try to get this person to get over in the passing lane. Unfortunately, this person did not, and he hit the TMA that Michael was in. TMA means truck mounted attenuator. And this truck pushed Michael over for 100 feet, and we were both taken to the hospital. In the end, Michael said he couldn't pick up his kids, he couldn't play with them, and all because of someone else's fault. And this is serious, and this is our life in danger. I bet that by now, if you are driving on freeway often, you should have seen this kind of maintenance vehicles a lot. We have different DOT have different maintenance vehicle, but those maintenance vehicles share something in common. Number one, they are doing a lot of maintenance work. They could be patching the potholes, or they could be doing the pavement striping. We have a lot of work that on the freeway, on the highway, that we need those maintenance workers, need those maintenance vehicles to come help. The second similarity is those vehicles, they drive really slow on the freeway because they are doing the maintenance, right? Typically, they drive at a speed of 8 miles per hour or 10 miles per hour. But if you look at us, right, if we are the regular driver on freeway, we are driving at a 70, 75 miles per hour. So that's a significant speed difference. That means when we see those vehicles, we have to recognize them right away. We have to start to decelerate and shift to the lane, shift to a different lane, right? If this doesn't happen, then crash will happen. So we know that transportation system maintenance is really important. Those are critical to the transportation infrastructure. Those are critical to our economy. However, doing the maintenance work could be dangerous. In 2020, US DOT spent $24 billion to preserve the national highway system. That's a lot of money. That's a big business. We have a lot of maintenance vehicles. We have a lot of maintenance workers working in the field. However, work zone is dangerous. According to the 2018 work zone numbers, there's a crash happens every 3.3 minutes in a work zone area. And every week, 115 people are injured at a work zone location. And if we look at the fatality, every week we have 14 people die in the work zone. Well, if we focus on the DOT workers like Michael, you will notice that Michael is not alone. Missouri has the statistics shows that every year in the state of Missouri, we have 16 DOT workers involved in the work zone crash. Those are specifically the DOT workers that are driving those maintenance trucks and are doing the transportation infrastructure maintenance. And in Colorado, this number is slightly lower, but still every year we have 7 DOT workers got injured. So DOT workers, when we talk with them, they even made a joke to us. They said they describe themselves as a sitting duck because they are driving a vehicle that is 10 times more likely to be hit. Well, I mean, this is serious, right? If DOT workers are concerned about themselves, then in the future, who's gonna do the maintenance work for us? So with that background, DOT has been heavily investing in the latest technologies to see that with the latest advancement of different kind of technologies, what can we do to protect the lives of those DOT workers? And today we're going to focus on a specific technology called Autonomous Truck Mounted Attenuator, ATMA. So this vehicle system has 2 vehicles. We have a lead truck and a follow truck. So on the picture, on the right-hand side, I'm showing the real vehicles from Missouri DOT. And you can tell that this is a brand new, but this is a typical maintenance vehicle. This vehicle, you can drive it out to the road to do the pavement striping, to do different kind of infrastructure maintenance. Well, the difference is if you look at the vehicle, it has multiple sensors. For example, you will notice that it has a high resolution GPS devices. It has a LiDAR devices. It has the vehicle to vehicle communication devices. So we install those sensors on the front vehicle. And if you get in, you'll realize that there are several screens on the lead vehicle. The drivers can very easily check out the system status of this autonomous vehicle system. There's also a camera showing the status. Now you can see the status of the vehicle behind you. So that's the first vehicle. And then we have a second vehicle that is following behind. We call it follower truck. And for the follower truck, we install TMA, truck mounted attenuator, on the follower truck. And this vehicle really does nothing but the car following. This vehicle does not perform any maintenance work. This vehicle merely follow the first vehicle. And the distance between these two vehicles are pretty much fixed. You can set it to be, say, 100 feet or 200 feet, whatever distance you like. And because these 2 vehicles, they are not far away from each other, and the second vehicle is really sort of a cushion or a buffer, then Missouri DOT say, why don't we remove the drivers from the second vehicle? And then, so the second vehicle can drive autonomously. And that's the idea. That's the idea that we really hope to remove the drivers from the second vehicle. So that if a crash is inevitable at work zone locations, I mean, due to whatever reason, if a crash is inevitable, the general vehicle will hit the second vehicle first. And because the second vehicle has a TMA component, and also because the second vehicle does not have a driver, then in this way we can reduce the fatalities to the DOT workers. So now I'm gonna show a quick video about a live demo of the technology in operation.
My name is Shailen Bhatt. I'm the Executive Director of Sedalia. The DOT exists for two reasons: to save lives and to make people's lives better. And today we're going to see it in action.
Thank you for joining the Colorado DOT in Fort Collins for the world's first unveiling of an autonomous work zone protection vehicle. This vehicle is designed, as you've heard if you listened to the previous press conference, to protect the workers in front of it from being injured or killed by any members of the traveling public that enter into the work zone. They have an extremely high precision GPS system that allows the position data to give us plus or minus 4-inch accuracy. That information is picked up by the following vehicle, and it matches position, it matches heading, and it matches speed while keeping a constant gap distance to make sure that it perfectly matches the maneuverability of that lead vehicle. Now, that 4-inch accuracy was extremely important to us because we want to make sure that when this is out in an operation, that vehicle is not straying from its lane. And that follower vehicle actually has a system mounted on the front of it that can detect objects, detect obstacles, and ensure that it can safely stop in time before it struck a car or a person or anything that might be in between the two vehicles.
Okay, that's a quick demo. Let me go to, let me go to the next one. Okay, so the technology has been rapidly being developed. And as I mentioned, I feel many DOT are already making a lot of investment in this area. For example, Colorado DOT is the first to deploy such technology starting 2017. And Missouri DOT is the second. Missouri DOT jumped in 2018. And then a few other states, including California and Minnesota, they have made a purchase of such a technology. And the other states, including Florida, North Dakota, Tennessee, and Virginia, they are in the process of testing out this technology, or they have already finished the testing. And in addition, as I mentioned, Colorado DOT start from 2 years ago to 3 years ago, they started a pool fund with 12 state DOT members, as well as a federal highway. So when we look into this technology, the technology is being developed by the industry. But if we look into the literature, if we look into MUTCD, if we look into the federal regulations and the industry standard, you can find out that there's pretty much literally nothing there. I mean, there's not much useful information that state DOT can use to, I mean, for different kinds of, I mean, in terms of how to test this system, how to deploy this system. So in my view, there are multiple research opportunities in this area. For example, in the first area is in terms of the system testing. That how can we claim that this system works well, and what should be the industry standard for such system? And we also need to ensure that whatever system that is being developed, it should align well with the federal regulation as well as the industry standard. And the second topic is a driver guideline and training. Well, those DOT workers, they need to have specific guidelines or a set of rules for them to operate this new technology. And thirdly is we need to analyze the impact of this new technology to the traffic flow, to the traffic efficiency and the traffic safety. And the fourth aspect is we need to analyze operational design domain, or ODD. Basically means that under what conditions, where and when can we deploy this technology? Certainly we cannot deploy this technology at any locations. That's not the case, right? And then we also, the state DOT also cares about deployment optimization, meaning that if they have, say, they have several roadway segments that they need to maintain, then what is the sequence of maintaining them? When should the DOT go out to maintain them? There is some research needs to be done over there. And then finally, since this technology is still at a pretty early stage, a systematic documentation is important. Today, due to the for the sake of time, I'm gonna focus on the three aspects. Number one is on the testing. Number two is on the driver side. What can we do for them? And number three is the ODD of this technology. So back in 2018, I came to Missouri S&T in 2017. So this was actually my first project when I switched back to academia. In 2017, Missouri DOT has IFP out. They want to deploy this technology, and I teamed up with hardware vendor, and we went together for this proposal, and we got it. So in this project sponsored by Missouri DOT, first of all, we need to review the national standard and the federal policy to make sure that the system specification that we came up with align with them, right? We don't want to do anything that is crazy, right? And after that, Missouri DOT purchased the trucks and the TMA and the other softwares, and they delivered to the hardware vendor. And the vendor retrofit the truck and deliver the system back to Missouri DOT. And after that, our job is to really help Missouri DOT test this technology. And this testing includes two components. The first component is 32-hour testing on controlled roadway. That means that is a controlled roadway with no or zero or with zero or very limited traffic with very limited traffic volume. And the purpose is to test, is to make sure that each component of this technology works and works as expected. And the second part is 250-hour live work zone testing, meaning that we're gonna really put this vehicle out there and do the maintenance work for consecutively 250 hours. So as we mentioned, that this ATMA system includes two vehicles. We have a lead truck and also a follower truck. The lead truck is doing the maintenance operation. And we, as we mentioned, we installed sensors on the first truck. So those sensors are collecting a lot of information of the first vehicle. And those information include the velocity of the speed, of the vehicle, the heading information, as well as the position information in terms of latitude, longitude, and the lateral information of the vehicle. And those information are collected by the sensors and through V2V, vehicle-to-vehicle technology, and those information are sent to a navigation computer. And then those information eventually is shared with the follower vehicle, which has no driver in it, and in the form of e-crops. And the follower vehicle will follow exactly the precise position, speed, and the direction of the lead vehicle. That is the way the system works. So to test the performance of the system, we designed a total of 31 test cases. Among them, 23 of them are quantifiable, meaning that we can use the data that we collect to quantitatively analyze the performance. And on the other hand, 8 of them are very simple yes or no question. Does it pass or not? Is a function there or not? So that doesn't involve a lot of statistical analysis. But our expected result is that we hope the system can function as expected. And the system, we hope it can pass the predefined criteria. And please note that there are two very important criteria. The first one is the lateral accuracy should be plus minus 6 inches. That means we anticipate this vehicle should stay in the middle of the lane, not go to the left, not go to the right, should stay in the middle of the lane. And the accuracy that we allow at Missouri DOT is plus minus 6 inch. And the longitudinal, the accuracy is plus minus 15 feet. That means if we ask the vehicle to be 100 feet apart, then the acceptable range is 100 plus minus 15 feet. In other words, somewhere between 85 and 115 feet. That is the range that Missouri DOT can accept. And for those 31 test cases, we repeat each one of them for 3 times. And we do this for a minimum of 32 hours. And as we mentioned, that we install sensors on the vehicle, so automatically those sensors get us a lot of data. On the lead vehicle, on the lead truck, it's pretty much a standard GPS information, including the timestamp, including latitude, longitude, altitude, heading, and velocity of the first vehicle. But on the second vehicle, on the follower truck, we are collecting much more information, including the gap distance, including the desired gap distance, and including the statistical information, and as well as a cross-track error, meaning the system accuracy, and also the steering amount and the state of the vehicle. So these two vehicles carries different information, and we are pulling out those data, we're comparing those information, and see that what is the system accuracy, how accurate and how stable does the system perform. We developed an evaluation methodology. We evaluate a system from 3 aspects. The first level is a system performance statistic characteristics, meaning that we are looking into the average system performance as well as a standard deviation of a system accuracy. We are also looking at 25 percentile, 75 percentile, that kind of things. So we do all of those in the first level, in the first stage, to analyze the statistical characteristics. And then in the second level, in the second stage, we analyze the system performance probability distribution, meaning that we put all the data together and we draw the probability distribution function for each test case that we want to look at. And the reason is that we really want to understand that if DOT set a certain criteria, then what is the probability of system accuracy fall into that area? Or in other words, what is the confidence interval? What is the confidence level of the system that is able to satisfy DOT's demand? And for the third step, we look into the hypothesis testing. The reason is that we are doing the testing minimum 3 times for each test cases. We are collecting a lot of data. And our hope is the system, the technology should behave consistently. If a vehicle works well in the first time, but it's not so good for the second time, that's not what we are expecting. We would expect the vehicle perform consistently every single time. So as a result, we develop null hypothesis, and we use the data to calculate the results. And then in the end, we're going to reach a conclusion, say the system is stable or reject such hypothesis. So we look, as I mentioned, we look into 31 test cases. For the sake of time, I'm not going to go through all of them. But following distance and accuracy, this is one significant challenge. I mean, this is one significant technical aspect that we're looking into. We want a vehicle to follow each other with a pretty good system accuracy. As we mentioned, the criteria is plus minus 15 feet. So we perform these following accuracy tests under different situations. For example, we test accuracy. We perform the testing on a straightway. We test accuracy on curves, on the ramps, and we ask the vehicle to change lanes, to make a left turn or make a right turn, and then again we pull all the data and we analyze the system accuracy under different kinds of conditions. And we also look into, for example, the communication loss. Due to whatever reason, the vehicle-to-vehicle communication may get lost. And if that happens, our hope is that the vehicle should continue to drive for just a little bit, maybe for a few seconds, with the hope that the vehicle-to-vehicle communication can come back. If it doesn't come back, then in a few seconds, stop. Otherwise, well, if a vehicle-to-vehicle communication comes back, then that's great, right? Let's continue. That's a resiliency that we hope to build in the system. And also, as I mentioned, there are a few test cases that is a simple yes or no. For example, we focused on the obstacle detection. We purposely threw the cones through the barrel into between these two vehicles. And so the system with the communication technology, the system should be able to detect such obstacle, and then start an A stop, and then stop the disengage the system. This is important for the field operation, because imagine that you may have a pedestrian, you may have a wild animal suddenly show up due to whatever reason, right? There are different kinds of exceptions. So we need to be well prepared for those special situations. And also emergency situation may happen. On the vehicle, there are multiple buttons, those emergency button, big red button. If due to whatever reason that emergency happens, then we can push the button and immediately stop the vehicle. Our hope is that the follower vehicle can catch up to the set distance and then stop or disengage from the system. And we hope that the distance error should be within a predefined criteria. So that's pretty much for the system testing. If you are interested to know the very detailed data, I would encourage you to look into a paper that we published recently on TRR, Transportation Research Record. It's online already. The third topic I want to talk about is a system operational design domain, or the ODD. So the motivation is that, as we mentioned, when we look into MUTCD, when we look into HCM or the other federal regulation, there's really not much in there. DOT, such as Missouri DOT, Colorado DOT, they don't really know that when and where should we deploy this technology. I mean, certainly we don't want to deploy this system on a very busy freeway during the peak hours, right? That's no point of doing that, unless absolutely necessary. So nowadays, DOT is using some simple numbers. For example, Colorado DOT is using 6,000 ADT as a cut. So if a road has lower than 6,000 ADT, we can deploy, otherwise, no. But then where does this 6,000 ADT come from, right? We have to come up with a scientific method to determine those values. And in terms of determining the ODD, we feel the most important thing is the length of the queue, as well as the delay of this, caused by this technology. So to calculate the delay and the length of the queue, there are a lot of classic traffic flow models that we can leverage on, right? I'm not going to spend a lot of time, but a very quick review. This is a typical, on the left-hand side, this is a very typical fundamental diagram. X is a density, Y is a flow. And we assume that traffic follows a triangle fundamental diagram. And if we have this fundamental diagram, then we can very easily calculate discharge rate, right? Discharge rate means how many vehicles can pass through the roadway segment in 1 hour. So discharge rate, which is this thing, this mu, the length of this mu equals to Kj, which is a jump density, times Vu, which is a cruising speed or free flow speed, times W. W is a backward wave speed, divided by V mu plus W. Again, VW is a cruising speed, and W is a back wave speed. And then in terms of the length of the queue, we know that when the demand, if we look at the right-hand side picture, we know when the demand is higher than the supply, or higher than the capacity, then the queue will show up, right? So the length of the queue is really the difference between arrival rate, which is lambda tau, and mu. Mu is the discharge rate. So the length of the queue can be calculated with the integral of lambda tau minus mu with regard to tau. And then once we have this length of the queue, we can calculate traffic delay, which is the integral of Qt. So that is pretty much old school, right? We can find that in the textbook. But now the challenge is we really need to look into the capacity or the discharge rate, because ATMA vehicles are moving on the road, right? If we are talking about two lane, if we are talking about highway with 2 lanes in each direction, before the roadway maintenance, we have 2 lanes each direction. So we are mostly talking about 4,000 vehicle per hour, something like that at discharge rate, right? If we don't use ATMA, if we close out one lane completely, then the capacity would drop to half, right? Because right now we only have one lane. But now we have ATMA, and ATMA are moving forward slowly. But in that case, we need to estimate what is the capacity, what is the discharge rate considering the ATMA, and that is really the key. And we formulate this problem as a moving bottleneck, because if you look at this picture, these two are ATMA vehicles. They are moving slowly. Again, it's not like this lane is blocked completely. That's not, if that's the case, then that's not good, right? But those vehicles are moving slowly. So they are sort of serving as a moving bottleneck. And we develop methodology to estimate this the capacity of this moving bottleneck. The idea is that we put a moving observer next to the ATMA system, and then from the moving observer's view, it's like the ATMA is stationary, because this moving observer move at exactly the same speed of ATMA vehicle. So for him, this ATMA vehicle is stationary. And before this ATMA location, there are two lanes up, and at this particular ATMA location, there's only one lane. So with that, we can very easily build this red triangle OGI. This is a fundamental diagram that this moving observer can see. But on the other hand, what we really need is the capacity from a stationary observer's view, meaning that if we stand at a particular location, if we stand still, how many vehicles can pass me within given amount of time? In that case, I am a stationary observer. So in that case, what we really care about is the black triangle O, G prime, and I prime. And the traffic flow theory tells us that the difference between these two triangles is the density times the speed of this moving bottleneck. So with that, we can establish the relationship between these two triangles, and in the end, calculate the capacity of this moving bottleneck. And once we do that, DOT can very easily calculate the length of the queue and the total delay. And we're also installing cameras on those ATMA vehicles to verify those parameters, to verify that is a model that we are developing really capture the traffic dynamics in the field. And this is the last section I'm going to touch base on, is on ATMA driver operation guidelines. The motivation is that ATMA operators, again, if we look into MUTCD, there's not really much in there. ATMA operators are not provided with much practical driving guidance, meaning that we know that the system has two vehicles, a lead vehicle and a follower vehicle. And this lead follower design imposes more requirements on the lead truck drivers. For example, if this ATMA system need to switch lanes from the right lane to the left-hand side lane, well, their behavior should be pretty different. If I am driving my own sedan or SUV, I look over my shoulder, I find a gap, then I'm gonna switch, right? And this gap, typically 2 seconds, 5 seconds is enough for me. But for ATMA systems, you need to think about not only the first vehicle that you are driving, you also need to consider the vehicle behind you. And also there's a gap distance between these two vehicles. And we want to avoid a situation that the first vehicle is able to finish the lane changing, but second vehicle continues to stay in that right-hand side lane. In that case, the system will not work. Another example is when the system crosses the intersections. If we are driving, we approach intersection, and the traffic light is turning from green to red. Well, if I can pass, I'm gonna pass if I'm driving my own sedan. But for ATMA vehicles, that's different, because because we need to make sure that not only the lead vehicle can pass, but we also need to make sure that the follower vehicle can also pass intersection altogether. That either you are making a left turn or right turn or go through intersection. You have to make sure that the entire system can cross intersection altogether. And finally, we also need to pay attention to the following distance setting. How far should this ATMA system away from the other vehicle, from the general vehicles? And what should be this gap distance between these two vehicles? So for the sake of time, I'm gonna go a little bit quicker. We borrowed the classic new wheel car following model from the textbook. We assume that the time-space trajectory of a following vehicle N is essentially the same as a leading vehicle N+1, except for translation, except for delay in the space and in time. And we also adopt the classic lane changing model that when a vehicle is changing lanes, it will consider not only the lead gap, but also the lag gap. But we are modifying those car following model as well as the lane changing model and apply it to the ATMA operation. For example, when the ATMA system is changing lanes, it needs to consider not only the lead gap, the lag gap, but also the gap distance between these two vehicles. And also, and when the vehicles are following each other, for the first vehicle, he needs this. For the first vehicle, the lead vehicle, it should not run into the vehicle in front of him. But for the follow, so there's a perception response time, right? Because the first vehicle is driven by human. But if you look at the second vehicle or the follower vehicle, there's no driver. So in that case, the human perception reaction time is really out of the picture. It's no longer a concern. It's no longer our concern. But instead, we should look into the road ahead distance, as well as the system accuracy. How accurate is the system maintaining that following distance? And the same thing for the intersection clearance time, we also modify the equation to make sure that ATMA vehicle system has sufficient time to safely pass the intersection. If it cannot pass, maybe the ATMA should wait. Our conclusion is that so we collect the data and we use those data to calibrate our model, to train our model, and we run different kinds of numerical analysis. And in the end, our conclusion is that for in terms of a minimum car following distance, the lead vehicle, the lead truck, should be minimum 75 feet away from the general vehicle. But for the follower truck, this distance range from 100 feet to 172 feet. And this values depend on the speed limit. And when we are talking about the lane changing critical gap distance, we need a minimum of 25 seconds to perform a safe lane changing with a gap distance of 172, and 27 seconds with a gap distance of 200 feet. And for a typical freeway with a free flow speed of 70 miles per hour and ATMA operation speed of 100 miles per hour, 10 miles per hour. And for the intersections, if a gap distance of these two vehicles is said to be 100 feet, then this ATMA system needs minimum of 15 seconds to cross intersection. If a gap distance is said to be 200, then it will need minimum 25 seconds to cross intersection. So those numbers are significantly higher than the requirement on the general vehicles. And as a result, we feel this is important to talk with DOT and to show them that when the drivers are operating this new technology, there are a lot of things we need to pay attention to. So with that, I'm gonna start my presentation here today, and then I'm happy to take any questions. Thank you. Okay, let me check into the message in chat.
Yeah, I don't see any questions in the chat room at this time, Dr. Hu. So we'll give a little bit of time.
So yeah, I'll ask one question. This is Xiaoming. So interesting presentation. I was just wondering, you focus so much on the traffic implications. I mean, capacity, safety, whatnot. Do you envision like the introduction of this type of technology will have some sort of impact on the pavement preservation or I mean, pavement life?
Well, to clarify that, because my area is transportation, so traffic flow and model and data analysis, that's my expertise. I do think that this technology in the long run will impact how DOT maintain the transportation infrastructure. We know that traditionally DOT, if DOT needs to perform inspection or perform maintenance, they will send the workers, DOT workers, to the field, right? They will completely block out a lane or even completely block out that entire roadway to do that inspection. But with the technology, as you have seen in the video, that we do not have to block out entire lane. We will have a vehicle that can drive slowly, and this vehicle can do the maintenance work, or even this vehicle can collect the data. For example, if you want to install a camera on those vehicles, and then the camera can capture the pavement conditions. Or if you want to install a LiDAR, and then the LiDAR may also be able to collect all those information about infrastructures. And so I guess to answer question number one is that I feel that we do not have to completely block out a road, and so that we can do the maintenance probably more often. And secondary, we can install the sensors to maybe help faculty like you with a good expertise in those areas to look into those problems.
Thank you. That's very good. I think there's a question in the this is Mustafa from WashDOT. Can you see the question or?
Yes. Thank you, Mustafa. And I think this is a great question, and we are actually working towards that direction, but somehow we are lacking. I think that for the snowplow, this is I talked with Missouri DOT and the industry vendor about 2 years ago. I think snowplow is a really good application. Because you know that in Washington or even in Missouri, as I mentioned, Missouri run is crazily cold. So snowplow is very popular, but a lot of times, if the road is covered with snow, we don't even see the edge of the road, right? So we don't see the pavement marking the lanes on the road. So sometimes doing the snowplow could be even dangerous. The idea is that Mustafa, if we can somehow say during the summer times when there's no snow, if we can have a vehicle to drive through those routes and collect the high resolution GPS information and then store them somewhere. And later on, when the winter comes, when the road is covered with snow, maybe we can have another chart, follow exactly that exact GPS location, and then go through that route again to do the snowplow. So in that case, we do not even have, we do not have to rely on our eyes to see the edge of the road, right? And we do not have to rely on the pavement marking or anything else, because we have those information already. We already have those information from the military-based GPS location. So we do have that idea coming up a few years ago, but somehow I think that we need a champion from the DOT to promote the technology and to really promote those applications. So I hope that answers.
Yeah, I think you're right. It needs some traction. No pun intended.
Yeah.
Jim, I see Jim Weston, my colleague, is also tuning in. Maybe he has some feedback. Jim?
Yeah, no, those were, I think Dr. Hu you hit that right on the head. There's work to be done. I think if mapping were in place, especially with the future of where GPS is at, it would be easy to do kind of like breadcrumb tracking in advance of everything instead of just immediate. We were part of the pooled fund study right now currently, this particular study, and it's exciting to see what's happening. There is, from my perspective, this is not the DOT particularly, but it's interesting to see the technology move so quickly in just the last couple of years, especially that some of the 6-inch variants down to 4, and being able to capture a break in between the two vehicles, like somebody crossing that system and the trailer vehicle with nobody on it, or the ATMA vehicle actually just stopping, recognizing that something is there, as mentioned in the presentation. It's really nice. We're also looking to see where this goes in conjunction with some of the new technologies for letting drivers making them aware well in advance of a work zone, and then even for some of the automated vehicles, seeing the technology that's coming around, kind of driving their automated vehicles out of that work zone lane without much effort. So it's interesting. This is a great presentation, and thank you for it. There's a lot of detail that was explained well. So thanks.
Thank you, Jim. Indeed, I fully agree with you. Snowplow is it's a commonly, it's a common problem for a lot of the northern states. So, but Washington is also in the pool fund, so you know that it takes a lot of it takes a village for the vendor and academia and the DOT to go to this far. So for the ATMA technology, that if we want to move towards the snowplow, I do appreciate that. Maybe when the COVID is over, maybe we can I can find you in a conference, and then we may talk more. But I do see that for the technology to move forward, the vendors they need a champion, and we also need someone to put the vendor, academia, and the DOT together, and then we can move forward, right? And if we have multiple DOT that are interested, maybe we can also put together sort of like another pool fund specifically focused on the snowplow or things like that. So.
You have another question in the chat box, Dr. Hu, from Christian.
Oh, okay. Okay, from Christine. Let me see. Or that it does not break down, becoming obstacle. For example, a sudden object comes in between these two trucks. Yes. So, so Kristen. So first of all, we build in the vehicle-to-vehicle communication between these two vehicles, and I believe the vendor also used the Wi-Fi technology, the radio communication. So there are we designed some what do we call the system redundancy. So just in case if one thing break, then the other things will kick in and avoid the system to go down completely. And secondary, that I remember that in the last year or in the first version of the product, if the system detect any obstacle, then the system would stop completely, and that's by design. And I do think that those features could be improved. For example, we are discussing, I think later last year we were discussing with Colorado DOT that if this system is driving, if ATMA vehicles are driving on the road, and if a general vehicle suddenly cut in between these two vehicles, right? By design, the system will stop, but that's really not necessary because this cut-in vehicle may not even impact ATMA operation. The vehicle may cut in and then quickly leave for another lane. If this process lasts only for a few seconds and really doesn't impact ATMA operation, then we may be able to let the system continue to run. But in order to make that happen, then we will need a lot of analysis in terms of the sensoring technology, and also some of the logic on the vehicles to decide under what conditions the system can continue to run, and under what conditions we should stop the vehicles. So those are the a lot of the improvement that we can do. In one of my project with the pool fund, actually the last one, system documentation, we are proposing to them that we will have a system needs documentation, meaning that for a lot of features, a lot of features like Mustafa and Jim mentioned on the snowplow, and also as you mentioned that for the improvement, for those improvement, the vendor may not have time to do it right now, or they may not have motivation to do it right now. But our hope is to, in the pool fund, our hope is to have a document that to have a living document those good discussions, so that later on, if we have any DOT wants to look into those area, or if someone want to champion for those efforts, we can share that document. There'll be centralized living documents, and then anyone can come in and take a look and see the discussion that we have. So hopefully that answers your question, Kristen.
Okay, I don't see any other questions. He did say yes, thanks. So apparently you answered his question. Well, thank you so much. If we'll give another 5 seconds if there are any more questions for Dr. Hu. If not, I just want to remind everyone that this webinar has been recorded, so it will live on. As soon as we get the recording, we'll put it on our website and our YouTube channel. So you just need to go to our website to access that. So we do have a lot of viewers who will see this in the future. So very interesting presentation. Thank you so much for your expertise and for everyone who joined us today. Any final words or thoughts? Doesn't look
Thank you,
like,
everyone.
yeah.
I would just like to humbly apologize. I had an autocorrect, it seems, from Dr. Who to Dr. Who. So my apologies. Yeah.
No worry, Mustafa.
Yeah. See, apparently somebody is more famous than you are, Dr. Who.
Mustafa, if you see me at the TRB, if we meet in person, I will laugh at you. You will laugh at me. We'll be good friends.
Thank you. Take care. Sorry about that.
Okay, well, thank you so much, everyone, for joining us, and hope to see you next time on our webinar for TriDurLE. Thank you and have a great day.
Thank you, Cheryl.
Thank
Bye.
you, Cheryl.
Bye.